Hello. In this lecture we will explore another AES encryption method. This is a combined encryption mode that is efficient and secure. It can also be easily implemented in hardware to achieve high speeds with low cost and low latency. GCM is a block cipher mode of operation that provides both confidentiality and data origin authentication. The GCM authenticated encryption operation has four inputs: the secret key, an initialization vector IV, a plaintext, and an input for additional authenticated data, AAD. It has two outputs, a ciphertext whose length is identical to the plaintext, and an authentication tag. The initialization vector is 64 bits, which is 8 octets. For a given key, the initialization vector must not repeat. The encryptor can use any initialization vector method that meets the uniqueness requirement. It is a responsibility of the sender side. We have seen this before in CCM encryption method. The key mat is used to derive the encryption keys for both the initiator and responder. The last 4 octets of the key, or 32 bits, is the nonce, also referred to as the salt. This nonce or salt remains constant for the life of the security association. The initialization vector is created at random by the encryptor and it has to be unique for any given key. There is 2 to the 64 number of initialization vectors that can be created, after which the security association must be renewed by a phase 2 quick mode or create child SA. To make the integrity calculation unpredictable, the GCM mode uses an additional authentication data for the integrity operation. The additional authentication data consist of the concatenation of the security parameter index and the sequence number of the packet. The outcome of the GCM integrity calculation is referred to as a tag. This is used for the integrity check value of the packet. GCM supports AES with 128, 192, and 256 bits key length. It uses the same concepts as its CCM counterpart. However, the message authentication code calculation is different. In CCM, the message authentication code utilized XOR of additional authentication data with ciphertext block 0 followed by an encryption using AES. The CCM used the key counter to encrypt the plain text chunks using the key counter. That is the nonce followed by the initialization vector in the 32 bits counter. The GCM uses Galois multiplication of the ciphertext of the previous round by the key counter for this round. Each round of ciphertext does the same until the last round, which produces the last message authentication code, MAC-N. This MAC-N is XORed with the length of the ciphertext, producing what is called a tag. This tag is the integrity check value of the ASP packet. It gets appended to the end of the packet and would be examined by the recipient to ensure integrity. Okay, so the other portion of this method is encrypting the traffic using AES, which is the same as in the CCM method, discussed in the last chapter. The plain text is split into chunks, each chunk is XORed with the key counter, then encrypted with ASCII IDE. The ciphertexts of each rounds are concatenated together and the outcome is the encrypted payload of the ASP packet. The sender sends the ASP packet with the initialization vector. On the decryption side, the IPsec peer receives the packet. It looks up the Security Association database to get the ASCII IDE, which also retrieves the nonce. It gets the initialization vector from the packet. It will do the decryption the same way we described multiple times. The only difference with GCM is its integrity check value validation. This would take the additional authentication data, it will XOR it with ciphertext block 0, the same way that was done by the sender. It will XOR it with plain text of block P1, which is the decrypted ciphertext of the C1 round. It will do Galois multiplication of that plain text chunk with the GF of 128. If you don't know what GF of 128 means, don't worry about it. It's a finite math calculation. This MAC is carried around through the round, and in each round it gets XORed with the plain text chunk. The final round produces MAC N, which is XORed with the length of the ciphertext. This will calculate the tag for this ESP packet. The recipient will then compare the received tag with the calculated tag. If the two values match, that means the ciphertext wasn't changed in transit. Hopefully this was helpful. We will discuss more in the next lecture.